Hello and welcome to this video for Electropages. I'm your host, Robin Mitchell. Today we're here at Avnet Silica in the UK and I'm joined by my very good friend Thomas Hauer, who's the man who knows power. And today we're going to be talking about packaging. I nearly said power then, but power packaging.
Okay, yes, power packaging.
Power packaging, fantastic. So packaging is, I think in many ways, it's almost like, I tend to see packaging as the connector of electronics in terms of the fact that people don't probably give it enough thoughts, or enough sort of like attention in electronics. Would you say that's probably a fair assessment or not?
Yes, because in the past the variety of different packages was not there as it is yet. Because in the past, when you were looking at a IGBT or high voltage superjunction MOSFET, it was like TO-247 done. So
yeah,
then D²PAK, D²PAK, and yeah, that's it. But now we have modules like the APECs, then we have top side cooling, dual side cooling, all this kind of other packages where you can kind of sinter onto heat sinks and stuff, and this gets more, let's say, variety, but also more complexity in what you can do actually with your mechanics, with your cooling and so on.
So for me, I think the biggest challenge I tend to find personally as an engineer when it comes to packaging is trying to figure out which ones actually exist. Because you've got, like you say, you've got so many different varieties out there. Sometimes it can be quite easy to miss the package that could be perfect for your application. So is this a challenge that you also see engineers face, especially in the field of power?
Yes, because often, let's say, new packages are not immediately visible at the supplier's website. And when you then go to customers, and I had this year customer visit where we're talking about the APEC, for example, from ST, it's a top cycle one. And they were like, yeah, we tend not to use single source packages. No, not really. It's not single source anymore. You have, like, in future, 5 suppliers going that route. And that's a different kind of discussion then, because they were like, oh, we need to investigate on that one because it's a whole new situation now.
And when you discover those new packages, that could massively transform your project, which could then result in smaller designs, more efficient designs, even easier manufacturing techniques. So in terms of, let's say the main, let's start off with the first two traditional sort of power devices, your IGBTs and your traditional silicon. In terms of packaging, how has that transformed over sort of the past few years, and where are we at the currently?
So automotive here again had a big influence on how this package thing evolved. So because there was the need for packages being able to handle a huge current, so 200, 300, 400 amps, and also there was the need to transport the heat out quite quickly out of the package to actually keep the die itself cool or within a range where it should be. And so suppliers and companies came out with things like the SD-PAK, that's actually a sintered package. Then the APEC, for example, which is a top cycle package, which is non-isolated. For example, then there's the APEC Smith, which is actually a tiny module, which is also top cycle but insulated. And there's the CC-PAK from Xperia, TC-PAK 5x7 from One Semi. So there's a huge variety now that you can choose from. Also, TO leadless is quite a new package that we see out there.
And how is the industry sort of coping with the introduction of things like SiC and GaN in terms of packaging?
SiC gave the whole thing a new direction because silicon carbide has, from a thermal point of view, better, let's say, parameters. So engineers need to come up with new versions of packages where it's easy to transport the heat out. And so sintering makes perfect sense because it's like direct connection to the heat sink.
Yeah.
But also top side cooling makes perfect sense. You need some kind of thermal interface material, but still you're way better than with traditional PCB cooling.
So just to be clear, in that top cycle, what you mean is that, like, if you've got your IC package, you've actually got exposed thermal pad on the top side.
Yes.
And that so like, traditionally you might have, like, let's say like a TO-220 part. You have sort of like that metal flange that comes out to the side, And then you can like mount a heatsink on there, or it can stand up and you can mount a heatsink on. But these top ones, you're saying that instead it's actually like a S&D part with an exposed thermal pad, and you can actually take heat directly from the top.
So for example, the HU3PAK or B-PAK or whatever you name it, actually it has an exposed pad on the top where there is one connection to the PCB, and then there's pins out on the other side. And actually the die is mounted right
upside down.
Yeah, it's mounted, it's processed upside down.
Yeah, I see what you mean, yeah.
And there are different versions. Some do wire bonding, some do copper clip with that. But with silicon carbide in there, you're really efficient in transporting the heat out of that. However, this is a good thing for kind of thermal transport, but it also imposes new kind of challenges for mounting, because with like TO-263, you were kind of bound to cool through the PCB. And with that one, you kind of have heatsink on top, and you can maneuver around on the back of the PCB like you want. But there's the thing. If you have, for a motor inverter, for example, you have 6 HU3PAKs, and you need to be sure that these 6 are perfectly aligned in height and perfectly, let's say, attached to the heatsink. So what you actually need to do is you need to have small cutouts in the PCB to have kind of plastic stamps pressing the thing.
So when it goes through, it will flex slightly, and that will mean any deviation between those parts will essentially be leveled out when you bring your heatsink down.
Yeah, you bring the heatsink down and you press the part itself, not the PCB,
right.
not the part.
So as in like you have a hole cut out, and there might be like a stud or something that will push it. I've never heard of that before. So but that's the kind of issue you need to worry about when dealing with these kind of high power.
Yes, exactly.
Because even though you've got that top side ability for the heatsink to come down, because of those slight millimeter changes, you've got to push from underneath. Make sure the devices come up.
Yeah, because it sounds silly, but every micrometer counts.
Oh, it absolutely does. It absolutely does.
And the thing is, you need to be aware that I see some approaches with spacers and stuff. These spacers have tolerances, so you cannot really rely on them. And so you need to press from the back, release, so not press on the PCB, because otherwise you have stress on the pins, which is nothing you want to have, and really press on it. And the same is for the APEC MIP, for example. It's also topside cooled, and there you need to press through the PCB.
And so if this is your chip, you'd have a small cutout underneath and a small something pushing through the hole directly onto the IC.
Yes.
And so that's an interesting question. So how does that not put pressure on the pins by pushing on the IC?
Because the thing is, you
mean the welding between the pads is what gets fatigued, but if you're pushing on the IC, it's the lead frame that's kind of like flexing with it, which is that makes perfect sense. Oh, I can see that.
So the package itself is quite precisely made, and so you always have quite tolerances. But if you press over the PCB itself, you make the PCB bend, and it's nothing you want to have.
And then you'll be pulling the IC in the wrong directions. It wasn't so essentially when you design those parts, you design them with being pushed in mind. So you design those tolerances for the flexing of for the lead frame, but you're not designing it for any kind of stress on those individual solder pads. Yeah, which does actually make a lot of sense. So when it comes to like that is how silicon and silicon carbide and GaN are seeing changes in this packaging technology, but what would you say is another major challenge that these technologies are facing when it comes to packaging?
You need to. So HU3PAK, for example, you have this package, and this package has a certain capability of die size they can take on. And for example, silicon carbide is absolutely fine, but there's also silicon MOSFETs in this package. There's also IGBTs in this package. And this, for example, for IGBTs, it limits the size. Obviously, for IGBTs, the more current they can carry, the bigger the die is. And so this limits the kind of IGBT capability in that package. Right. So that's a bit of a challenge. And for designers of that circuit, like this direct sintering packages are not easy to kind of process in manufacturing, because you need to be sure that this sintering is done right. every temperature angle you can look at must be right and everything. So it's really complicated, and not many companies are able to do it properly. So that's why it's always difficult with these packages. So I had conversations with customers, and they really wanted to have the package, and it's like you're producing like 1,000 PCBs a year with that, and I'm not saying they cannot do it, but I see the problems they're facing in production, and it's just not worth it, really.
And so does that mean that there are packages out there that require specialist care when actually using them?
Absolutely, absolutely. The direct sintering packages are some of them, and they're coming out of the automotive corner. And in automotive, there are lots of engineers there to solve the problems. For small to mid-range industrial companies, so it's not that many engineers that can think on the problem, and it takes huge effort and time to get this thing right.
So direct sintering, what exactly is that?
Actually, the part is not directly connected to the heat sink. It's really sintered on it, like.
When you say sintering, I'm thinking of like heat treatment. So you push two things together, they sort of form a bond. Are you saying
that exactly? You push together, right temperature, right pressure, and then it's like really sticks on it.
Oh, right. So this is about bonding the heatsink to the part, and this is not about. Okay, so manufacturing the PCB itself would be okay because any sort of reflow process could attach those parts.
Yeah.
But when it actually trying to stick the heatsink on there,
it's complicated.
And it's not a case of let's just put some thermal paste. So this is a really interesting question, and I tell you what, I know exactly where I see this a lot, which is actually the sort of the consumer market in gaming computers. You know, when you have like high-end processors with heat sinks and trying to get thermal mass out of the processor, that's always been a massive challenge. And it sounds like to me that could also be an equally difficult challenge, if not worse, in GaN and SiC technologies. Certainly when dealing with high powers like large chargers or some sort of sort of like large power converter.
With silicon carbide, I mean, you have packages that solve the problem already partially for you. For example, the APEC drive package, for example, it can come with fins, cooling fins, and actually the whole package can be screwed to the heatsink, and it's made for cooling liquid being flown underneath it.
Really? Yeah, so you've got an air heatsink above?
No, it's really a metal, aluminum piece with. It has a hole in it, basically, where liquid can flow through it. You screw the module on it, and then you make liquid flowing through it, and you have automatically the cooling. And everything between the die and the cooling fin is already optimized by the supplier.
So when we compare these GaN and silicon devices, silicon carbide devices, to like these sort of high-end processors which have to deal with these heat issues, would you say that in terms of energy density, like the GaNs and the SiCs, they're going to be dealing with a lot more per square millimeter, do you think?
The energy density is, of course, bigger with SiC and GaN, but it always depends on the overall size of the thing. Because when we're talking energy density on a flyback, it's obviously a small device and it's obviously energy dense, but it's less complex than, for example, Vienna bridge rectifier, dual active bridge, 25 kilowatts for a DC charger, because the whole system is like huge.
Yeah.
And so there's different, let's say, complexity levels due to application and topology. So I wouldn't go as far as to say, okay, this is that one, this is that one, this is that one. That would be too general, I would say.
And I think one thing that I'm sort of going through my mind at the moment, thinking of different packages that these devices can come in. And I think one mistake I'm making myself is that in the past, when I think of power devices, I'm always thinking of chunky heat sinks, large metal sort of thermal masses to bring the heat out, large pins and all that jazz, like the TO-220 type devices. But then when you introduce things like SiC or GaN, you really do start to look at things like QFNs and these sort of very small.
With GaNs, yes. Very small ones.
Very small packages. And so it's quite incredible to see how such a high power device can sit in such a small package without having issues. I mean, how does heat dissipation work in a situation like that?
With QFNs, you can have a center pad in the middle where you can transport heat out of it. And in the past, if you look at TO-247, for example, the die as a whole was bigger. With GaN, you have a small die, so smaller packaging options make sense, so you can stick it in. And GaN itself, for Flavic, for example, or for back converted, it's a switching losses that get smaller and smaller, and then
and therefore the amount of energy waste is less, so you can reduce the size of the package. So even though you're dealing with very high, because you're dealing with high efficiencies, you can have a really tiny package that only mildly gets warm when it's dealing with a much higher power. But because a lot of these devices, especially silicon carbide, has a much better thermal conductivity characteristic, does that introduce challenges when it comes to things like reflow manufacturing?
Not that I'm aware of.
And so even though,
I mean, silicon carbide has a higher temperature capability anyway.
But I think doesn't GaN have less though?
No, compared to silicon, it's fairly equal.
About sort of 75, 80 type degrees maximum, would you say? Is it sort of, or are we going beyond 100, do you think?
Silicon devices go to 150.
That's true, industrial, of course, okay, fair enough.
When it comes to top cycle packages, TC-PAK, for example, the 5x7, and there's a bigger one coming from onsemi. onsemi uses this for the T10 technology they have, so low voltage MOSFET, so 40, 60, 80, 100-ish volts. And actually the interesting point is, and what I always need to mention is, the package is in height 1.15 millimeters. And
wow, that's tiny.
If you use a gate driver that comes within an SO8 package, you're in trouble because the SO8 because the SO8 is almost 2 millimeters. So it's like,
that's insane. So you'd have to put that thing on the underside, but then you've got the issue of getting the signal to the chip, which means you're going to have parasitic inductances, you're going to have signal timing issues. Oh wow! So these manufacturers are making these things really tiny, but then they're kind of making them too small, too fast, to the point where the gate drivers can't catch up with it.
And the gate driver, I mean, there will be packages that kind of go
but
there.
Still, it's still an
issue. It's a fun situation at the moment when customers look at it. It's like, okay, but be aware the SO8 one gets you into troubles.
And that's interesting. So when you create it, so when these manufacturers of these power devices create like a reference design, for example, they'll have to design that reference design in a way that shows you put the chip here, this capacitor goes here, this driver goes here, but then they need to consider the heat dissipation. And if they don't go, well, actually, okay, we'll put this heat sink in, but that's going to clash with that sort of SOP-8 part, it becomes an impossible design. So
I would not go that far as an impossible design. Meanwhile, you can really...
Improbable.
So getting wires is obviously not ideal, but it's something you can handle because you can work with gate resistors and so forth. So it will work, but you need just to consider, okay, the one needs to go on the bottom side, the other one on the top side, and just reconsider, okay, do I need 12, 10 MLCCs there? Because they will kind of make an issue there as well. So it requires more thinking. And I mean, thanks to the help of modern PCB design tools, you can easily spot the issues in their 3D view and stuff. But packages advantages sometimes really get into funny directions where like, okay, that's then something I wasn't kind of taking into account there.
And again, I've seen some really crazy sort of package designs that come out from all kinds of different companies. So, would you say that with these new technologies, are we seeing more what I would call unusual package shapes, or are they kind of sticking to the more standard types?
At the moment, I would say unusual shapes or pinouts are still sort of common, if I can say common, with GaN, because every supplier sticks to their own kind of pinout and stuff. For the silicon carbide, actually, some suppliers have a sort of platform approach. For example, ST is quite clever in doing that with the APEC because you get their DM and M6 technology, you get their silicon carbide, you get their IGBTs in there. The same is for their APEC SMIC, because the APEC SMIC can handle or can have the DM6, M6, then also IGBTs, then silicon carbide. I think they have thyristors in there as well and some diodes. So they're trying to kind of
bring it all and almost standardize that type of design so that you can almost pick and place essentially as you need.
Yeah, and it also is kind of easier for the designer because they just need to just need to learn to play one piano, not many.
Yeah, so you don't need to worry about how to do two different types of D²PAK. You got it's a one D²PAK package. Everyone uses the same, so you know how to lay it out. You're used to the writing. But that raises a really interesting question, because I know that especially with that recent semiconductor shortage that we had a few years ago, and the fact that things like GaN and silicon carbide, you know, that they are relatively new technologies for what they are and what they're offering. One of the concerns I would have is that if you've got so many different package options, it almost limits you to a specific supplier when you kind of pick a device. And if you have so many different packages, it's hard to sort of find alternative sources, if that makes sense.
For silicon carbide, this situation eases because some suppliers pick up ideas from others and release in packages. So what I do see at the moment is a big trend in more packages per supplier, and it's emerging vice versa. And we're back to like really performance comparison and not package comparison. Yeah, there are some packages that stick out that's still quite unique, but they're getting rarer and rarer, really.
So here's an interesting question I want to actually ask you, because in terms of the number of manufacturers who are designing their own silicon carbide GaN devices, IGBTs, and I've always wanted to know the answer to this: is a package intellectual property such that if a company designs their own package, nobody else can make one that's compatible?
Some of them are, yes.
And so does that introduce challenges to engineers who want to pick a particular technology but find out that it really does lock them to one vendor?
Yes. That was initially, it was, for example, the APEC Smith is one of these cases because it was just ST producing it with silicon carbide and our MOSFET technology, and not other suppliers were not picking it up. So customers were quite reserved about this package. They were like, yeah, it's cool, I see the advantage, and I kind of want to use it, but it nails me down to you and that don't have a second source in case something goes wrong. And I mean, there's the option of getting this thing as a, what is it, JEDEC standard. Like the TO-247 is a standard package. But some of the packages are really private intellectual property, and the semiconductor manufacturer needs to license that one.
And do you think the reason why these, why do you think it is a lot of these manufacturers have shied away from those JEDEC standards?
It's not shying away. We had, with one automotive OEM, 2 important packages coming into the market, and these then got a big push. So that's got a big interest because one automotive OEM is using these 2 packages, and one is quite popular at the moment. And so this is a kind of, it's not a standard, an open standard. You need to license that one.
But like, why would, if you're a manufacturer of let's say a silicon carbide or a GaN device, and you've got to put your die in a package, why would you develop your own one over, say, using one that everyone else kind of has access to?
You do this mostly for one big customer that asks you for a package that has this or that kind of performance, shape, size, whatever. And normally it's like, we're delivering this to this one customer, and after a period of time, we're kind of allowed to sell it to the broad market.
And so that company develops the package. Like they'll get like a specification from that big customer, and they'll say, well, we need to have wings, we need it to have like a really large heatsink on the top. It's got to be able to do this. They come up with a package concept in exchange that after, let's say, like you say, a year or 2, you can then turn that into a package that you can offer other customers. And so it really comes down to an application need that kind of creates that package. And then you realize the package is really good, but then you realize it not, but then you've designed it and you've put the money into it, so you don't want anyone else to do it. But then I can see that being an issue. So do you think that if more of these manufacturers start using more common standards and collaborating with each other, do you think it might actually help engineers with their designs?
I mean, I do see the point where a supplier says, look, I put money into this and block it, but it's always the case if you have a big OEM, you're not a single supplier strategy there. So you have a second supplier who needs to be able to support that package as well. And this one pays then fees to the other one.
But this is something I've heard. I think this is something I've actually heard before about silicon carbide and these new technologies, which is that one company who produces a silicon carbide device, the properties and the characteristics of that transistor could be very different to the next most compatible device. Like they're not going to be completely drop and place compatible.
That's true. That's always a thing I try to make people aware of, because you just need to kind of open like 3-4 data sheets of different suppliers, and one has like gate resistance of 1.2 ohm, the other one 2.5, and the other one 8.
Yeah.
So there's a big difference. And if you kind of have the 8 ohm one and swap it with a 1 point something ohm, you need to look at EMC again, because there's a significant different switching behavior. And so big OEMs or automotive OEMs looking for the best performance part, and suppliers are then positively pushed over boundaries and try to figure out how can we make these things better. So I see this development positively, because it gives a push into new technologies, into new directions, and after some time, all the broad market draws kind of the benefit of these new developments.
Yeah.
And as we've seen in the past, it always takes one with a good idea and some market power.
And so you need that differentiation, the ability for people to design their own packages, so that if someone stumbles on like the best design ever conceived for that type of technology, then give it 5 years time, and then everyone's going to be starting to produce it. But it's also interesting you mentioned about the variation in devices in terms of, let's say, like gate resistance, because that's a very good, I would say that's a very good sort of like case where having smart programmable gate drivers that can modify themselves to varying technologies, so that, let's say you have to source from a different supplier, even though the package could be the same, the gate driving requirements are very different, but then you could program your gate driver to then behave differently, so that way you could cope and maintain the design.
Yes, in some. So when it comes to switching, the programming is done by gate resistors, so it's quite easy.
Yeah.
And there are actually already programmable gate drivers in the market. So for example, the SD-GAP4 is a very complex device for automotive. It has an SPI bus where you can program switching gap times. It has an onboard A to D converter. You can I think you're also able to program the protection, so you can vary between silicon carbide, IGBT, and stuff. So there's lots going on in this device. I mean, it's normal data sheet for gate driver is like 25 pages, and the SD-GAP4 I think is 70 to 100 pages.
That's a lot.
That's a lot.
That's a lot. So Avnet Silica, you guys are, your core capabilities is finding the right devices for your customers, which also means that you're going to probably have some of the best knowledge on things like packaging.
The best knowledge is always with the suppliers.
With the suppliers,
try to catch up.
But you try to catch up. But the point, actually, I would say that each supplier has the best knowledge on their own packaging.
Yes.
But you guys are going to sort of like have that broad knowledge where you're familiar with everything. So my first question on that front is, what would you say is the most common package that you've seen for these new technologies?
The TO-220 is one that gets really traction at the moment, especially for industrial applications, and another one is like APEC 1, 2, the module packages. They're still quite popular.
And that's something I have noticed a lot about these sort of newer devices. They do tend to come in modules and sort of like pre-made units that you sort of place into a circuit. And I take it that's because these devices need a lot of other support from other components for them to actually function correctly.
Modules take some of the thermal and layouting issues away from the engineers. And with modules, you have space like this, and you can really make it full of silicon carbide. So, and the newest trend is injection molded modules, where you have like really good single side or dual side cooling, so you can make a sandwich construction in the heat sink. And I mean, imagine this kind of construction being 1200 volt silicon carbide and having 2 point something milliohm of RDS(on). That doesn't come from a single die. That's multiples being in parallel.
And that much, and trying to design that yourself on a PCB would basically just be an impossible task. But on modules, you can achieve that. You get really good power densities, and it's in many ways more cost effective because it's already done for you. So you just place it straight in, provide it with power, and it will control. As long as you've got a suitable gate driver, it's going to behave as needed. So that's very interesting to hear that modules are Because I have seen a lot of modules in like PCIM, for example, they do sort of show up a lot. But in terms of, so in terms of sort of like sourcing and stuff, so let's say an engineer is sort of like, they want to use a GaN or a silicon carbide device in their next project. And they're kind of like unsure what package to use. I'm guessing that they can go to you guys and say, look, I need a new device, but I'm not sure what package I need. Is that something you guys can help with?
Yes, absolutely. We look then at what they're aiming to build, in what like housing it goes, what their overall constraints, limitations are, and then we just try to go on with that and say, look, this and that package makes sense. That one looks like it makes sense, but, and then you just go on from there.
And so if you had to give advice to an engineer before they start a project when it comes to choosing a package, what would you say that's the first thing they should do?
Call us. It's quite simple.
As simple as that. Don't even have a thought for yourself. Avnet Silica will do it for you. That makes a lot of sense. So, okay, so like you say, go straight to the distributor, go straight to your supplier, go straight to whoever it is who's going to be involved in your supply chain and get their advice first. And so, like you say, send an email, send a call, and then that way the engineer can sort of like say, okay, I found out about some new packages and stuff. So I suppose on that note, the last question I would say is, before we wrap up this video, if an engineer is out there watching this video and wants to get involved with Avnet Silica Solutions and what you can offer to them, what would you recommend that they do?
Send us an email over the website, find us on LinkedIn, give us a call. If you have a responsible Silica salesperson already, just give this person a call, and they will then forward us the need, and we then try to make a meeting with the customer and figure this stuff out for them.
Fantastic. Thank you ever so much for taking the time to see us today.
Thank you.
Thank you very much.